Hi, my name is Teresa. I'm from the Czech Republic, but right now I live in Miami, Florida. It's very hot here in Florida, about 85 degrees today. So let's go back inside to analyze the video. This is a screenshot of my analysis of the video in Tracker. I have selected the front wheel of the right foot as my object, and I've placed the origin of the axis on that wheel, and I tilted the axis by 1 degree to account for the trajectory of the motion. I have then tracked the center of the front wheel throughout the video. To provide Tracker with a scale, I measured the distance between the front of the front wheel and the back of the back wheel to be 34 centimeters, and I put the scale bar in Tracker as demonstrated here. Let's play the Tracker analysis. Here we are in Excel. I have listed all of the times and the observed positions as calculated by Tracker on the left hand side, and I calculated the initial velocity as the difference between the two positions in the x direction and the difference of time, and it came out to be 4.872 meters per second in the negative direction. To model the motion of the skate in the video computationally, I used Vidle. I set the system mass to be 65 kilograms, which is my mass since I'm the object moving through the video, and I set the initial position of the skate at 0.005 in the x direction as predicted by Tracker, and then I set the velocity to be negative 4.872 as calculated previously. The next few parameters that I'm changing are really where the Newton's laws come into play. So if we look at the net force, we see that here it is set to 0 in all directions. That means that there is no net force applied to the skate, and the skate moves at a constant velocity. And what the model does is it takes the position and the velocity of the ball at a certain moment, and it computes the position and the velocity at a moment later. And we have the velocity of the ball here, and at the next time interval, what we want to figure out is how the velocity changes, which is really this term that explains it. And we can see that if f net here is 0, then this whole term is going to be 0, giving us a constant velocity. For the position, we see here that we have the initial ball position, and then we multiply the ball velocity from here by the change in the time interval, and we end up with a new position of the ball, and then we take that position to be the initial position for the next computation. And this is what the simulation looks like when the code is run. And what we have here is the fact that the ball runs off on the left side from the workspace, and since this is my first time working with Vidle, I don't really know how to fix the dimensions or how to scale the workspace, so maybe that's something I can learn next time, hopefully. Last but not least, this is a graph showing the predicted motion of the skate in red versus the Tracker observed motion in blue. And what we are seeing is a pretty good agreement between the two data until about 0.4 seconds, when we see a deviation of the observed values from the predicted values in the model. And we can see that the displacement is getting smaller and smaller as the time goes on. And this can be due to a couple of reasons. Either we see a shift in the y and z direction of the motion, which is skewing the values of x direction a little bit, or, and that is probably more likely, the skater is actually slowing down, which means that there is a force acting upon the skater, and the Newton's first law of constant motion no longer applies.